Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to have a discussion on specific properties of benzene molecule now that we have been using it as our representative element in discussing of course, physical and chemical properties of other aromatic compounds. These are going to assist us, of course, why benzene and other similar ring systems behave in a unique way as they do. So welcome to the topic. So as I've said, we're going to look at the properties of benzene. And these are going to assist us in inferring or trying to determine other properties of similar ring systems, which of course are referred to as aromatic. So these are properties of benzene. And basically, as we're going to look at the properties, of course, this is going to also touch on what we've discussed, of course, but it's going to be relevant for us in this discussion. So we're going to look at the structure, the concept of stability, and also we are going to look at how benzene, of course, reacts with other elements or in specific conditions. So we're going to look at the concept of reactivity, and then lastly we will look at the reactions that happen directly on the, of course, aromatic ring, and that is going to fall under this. Of course, we're going to look at the two specific categories, that is for electrophilic and that is for nucleophilic, maybe specifically electrophilic reactions and the substitution one. So for that case, these are going to form a basis for our discussion that is concerning the structure, stability, and then the reactivity. Now, as we have been mentioning, without going into a broad part of the properties of benzene, we basically say that benzene is a liquid at room temperature. This is a liquid at room temperature. Just keep it in the form. It's a liquid at room temperature that has got, of course, low melting point, boiling point, and stability. So in this case, as we try to look at this, so it has low melting and boiling point, and even stability. This is in polar solvents. This is low stability in polar solvents. Therefore, we are going to see on our different ways. When we were trying to discuss about the concept of hydrogenation, we saw that comparing the aliphatic and aromatic compounds are quite stable in the sense that they require this reaction to take place at a very high pressure, which of course is for aliphatic compounds like alkenes, of course, it happens at around 1 atmosphere, compared to benzene, where hydrogenation for this compound, hydrogenation occurs under the condition of 1 atmosphere, whereas for benzene, of course, it occurs at around 150 atmosphere. And this one gives the inherent stability of these benzene molecules. So in the absence of polar substituents, benzene or the arenes are typically hydrocarbons. Now when we are trying to show the hydrogens that are bonded, of course, to the benzene ring, we had this structure. So I'm just going to put it for illustration. So we had this structure whereby these hydrogens are attached at these specific parts of the arene molecule. Sorry for that. So when we look at this structure, of course, we say that in the absence of polar substituents, the aromatic ring of benzene actually has a structure that is of a hydrocarbon, which is basically a compound that consists of carbon and hydrogens in this structure. This is similar to the alkane and alkene series, and even alkynes. So because they don't have another substituent or polar substituents, like for instance, if we put a nitro group there, or maybe them having a di substitution for hydrogen, we have a chloro or ammonium course, substituent there, then therefore this structure is going to be regarded as a hydrocarbon if this is hydrogen and this is hydrogen. So therefore we expect it to have some characteristics of just a general characteristics of other hydrocarbon, but we're going to look and see it that it's going to behave in some unique ways, therefore giving it its characteristic. Now that I've drawn this structure on the board, of course we had said that benzene can be represented in specific ways by giving two specific types of structure that we call the Kekulé structure and the Robinson structure. So I'm just going to also do an illustration for that. So this Kekulé structure can be written as the first one, so structure number 1 or 2, or this benzene as well can be represented using the Robinson structure, that is structure number 3. So in that case, of course, benzene as a molecule has got a planar cyclic conjugated structure, and we've talked of 3 concepts here. First, that it is planar, cyclic, and then lastly it is conjugated, which are some of the basic conditions that we talked which have to be met for an element, a molecule to be regarded as an aromatic structure. So for that case, it is planar, which means the atoms lie in the same plane, and then it is cyclic, which means it's an enclosed structure shown, and then it is conjugated. Now the concept of conjugation refers to that the molecule has got each atom which has been either sp2, now for conjugation or conjugated structure refers to a molecule that has got atoms which are sp2 or sp hybridized. So in that sense, benzene obeys that specific rule. And the concept of a planar, as I've said, of course, refers to the station or the state whereby there's a good overlap for interaction of the 2 orbitals. So that one gives it the stability that we have already discussed. So in this case, of course, we find that the benzene has strokes of single and double bonds, which of course we are seeing them alternating in the structure. But of course, whenever it is represented as this Kekulé structure, of course we are able to see that, and this Robinson structure is a general representation of that. Now conjugation, as I've said, that each atom of course is either sp2 or sp hybridized. And then as far as stability is concerned for benzene, so we are going to look at the concept of stability. For stability of benzene, as we have said, that aromatic compounds are of course stable compared to the other fatty compounds, which of course may form what we had already mentioned in our discussion in the beginning, that whenever it is there's lacking absence of polar substituents, of course it's just similar like the alkanes and alkenes, which are referred to as hydrocarbons. Now the aromatic characteristic of benzene, of course, infers an inherent stability to the system, and this makes benzene, of course, not all that reactive. So the aromatic structure or the aromatic nature of benzene makes it to be more stable. Therefore, this one gives it the characteristic of being particularly less reactive as compared to other alkenes. So in this case, this stability can be expressed through its so this stability of benzene can be expressed through its resonance energy. So this can be expressed through resonance energy of benzene. Sorry for that. This resonance energy, which is around 48, or this is 49.8 kilocalories per mole. So in this case, compared to other similar, of course, compounds, this is a large amount of energy, which shows that benzene actually infers as an inherent stability structure. So So in summary, there also, when we try to look at the reactivity of benzene, we're going to look at two different categories of reactivity which we can associate with benzene. Of course, the first one is a reaction of electrophiles directly on the aromatic ring. So this is a reaction of electrophiles on the aromatic ring. And then number two, we're going to look at the reaction of substituents. The reaction of substituents. Substituents. So now for the case of substituents, we are going to see that since the neighboring aromatic groups influences the reactivity, now the substances are going to have a different or unique way in which they are going to react. Now that they are being attached to the benzene ring, if I give an example for the methyl group that is attached to the benzene ring, we're going to see that the influence of the aromatic structure around this methyl group is going to influence on how that substituent is going to react. Now that is a statement that basically refers to the second statement about the reaction of substituents. Now for electrophilic substitution reactions that we are going to see maybe on the benzene ring, this happens because of the carbon-carbon double bonds of the arene molecule, which of course are going to interact with the electrophile, which we can generally denote as that. So in this case, this is going to react with the electrophile in order to form a product that is electrophilic, and substituted product, which is going to appear like that. So in that case, of course, we are going to have a substitution for that, and we're going to see that substituents as well can, the first substance and for di and polysubstituted benzenes, they're going to influence the subsequent substituents that are going to come in the arene molecule, and we're going to refer to them as directing groups, but that one we shall have a discussion in a different video. Now also we're going to look at the reaction directly on the aromatic ring and try to see what are the behavior of benzene when molecules are reacting directly on the aromatic ring. So for that case, these are reactions directly on the aromatic ring. So direct reactions on the aromatic ring will have three conditions. Now that we know that for cyclic, for arenes, the cyclic area of the pi bonds that we talked about is a region of high electron density, and therefore the arenes are typically referred to as nucleophiles due to the how can I illustrate it? Yes. So the first, for that case, the first condition is that we know that there are pi bonds, the cyclic array of dead pi bonds around the ring. This one gives the essence of a high electron density, which of course makes this benzene molecule to act as nucleophiles. So they are typically nucleophiles because of this particular characteristic. And then number two, we're going to see that unlike alkenes and alkynes, which of course undergo addition reactions, for arenes, of course, they undergo what we call so they prefer substitution reactions. They prefer substitution reactions to addition reactions. Or they prefer substitution reactions instead of addition reactions. Of course, in which some groups, specific groups like the hydrogen that we saw around the benzene ring are replaced by the other groups. And this one ensures that the aromatic system is retained. It's retained because of the stability that we have talked about. Now, Thirdly, for the reactions directly on the aromatic ring, of course, as we have said, basically it's the same concept that the substitution is preferred on behalf or in place of addition reaction, which of course will destroy the essence of aromaticity and its abilities will be compromised. So in that case, of course, for benzene molecule, those are some of the properties that we have of course looked at, which are going to form a basis for our other next discussions on basic aromatic compounds in as far as their reactions and chemical properties are concerned. So that is it for today, guys. I hope this is going to assist us to remember some of the concepts when we mention about the reaction on the direct reaction on the aromatic ring and the electrophilic substitution, electrophilic and nucleophilic substitution reactions, and other reactions which are going to occur on the benzene ring, like the Birch reduction, etc. So that is it for today.